what is a well-designed suspension, right? A well-designed suspension is vital for a good performing car. So these two lines define what we are expecting out of a suspension, right? So our purpose in designing the suspension and steering is to maintain the wheels at optimum angle to the road and surface at all times and under all conditions. What he means to say over here is that if this is the wheel and this is the road, the angle between the wheel and the road is critical. So this is a three-dimensional drawing. So what we would try to do is to maintain the angle between the wheel and the road. These mainly we are dealing with two main angles over here. So I'm assuming you know the basics of vehicle dynamics. So what we are trying to do is maintain the camber and the toe angles of the road to an optimum level. So this is the keyword over here, that as your vehicle goes over different types of road surfaces, as your vehicle goes in different maneuvers, you would like to maintain the camber and toe angles of the wheel with respect to the road surface at an optimum angle. So what is the optimum angle? The optimum angle is the angle at which your tire produces peak force. If your tire produces peak force, you will be able to accelerate, brake or corner at the highest G level, because most of the times the car performance is limited to the maximum force that a tire can produce, and the amount of force that a tire can produce depends on the suspension design, which again depends on the camber and the toe values that your suspension kinematically gives out, right? So as a design engineer, you're supposed to know what are the camber values and what are the toe values at which your suspension or your tires would produce peak force, right? So we would like to control the camber and toe under all times and all conditions, right? So over an infinite number of road conditions as well as an infinite number of maneuvers. So you can have any combination of acceleration, braking and cornering, and you would like to control your suspension kinematics under all these conditions, right? This is the holy grail of the designer and is in practice unattainable, right? So maintaining the optimum angle of the wheel with respect to the road, the optimum angle with respect to the road under all conditions is impossible. Under all conditions is impossible, but we can still try to maintain the best possible compromise that is possible, right? So this will make a lot more sense as we go ahead, right? So just understand this from this slide, that we would like to control the camber and toe values of the suspension so as to improve the forces that a tire can produce, right? Let's see how we can control the camber and toe, and at what values of camber and toe does a tire produce peak force, right? All right, so now we narrowed. So the first slide was about all suspensions in general. Now we go ahead with one particular suspension, that is the double wishbone suspension, right? The double wishbone suspension has been universally adopted throughout racing. So you will see that most of the race cars use a double wishbone suspension. So we will focus all our efforts on understanding the double wishbone suspension as well as optimizing a double wishbone suspension for your application, right? The advantage of using a double wishbone suspension for BAJA and FSAE is that both your front and rear suspension can be of the same design, right? except for the toe link. So what you can do is that, so there are different components as you can see in this diagram over here. The lower control arm, LCA, the upper control arm, UCA, upper control arm, and this is the knuckle or the upright on which the wheel is mounted, right? So these three components can be the same between your between your front and your rear, right? So you will have to make four parts, four LCAs, four uprights, and four UCAs, which you can use on each corner of the wheel. So each corner of the vehicle. This is a big advantage for students as they don't have to design new parts for the front and the rear, right? So this is why most of the teams use a double wishbone suspension for the ease of manufacturability. The second reason is that a double wishbone suspension gives you a high level of optimization control. That is to say that you can vary different parts. That is to say that these points, which are called as hard points, points of attachment, like this point, these points can be varied significantly without affecting kinematics or compliance of the suspension. So what you can also do is that I have seen some teams also use a McPherson strut both in the front and the rear. The problem with the McPherson strut is that there is a higher level of compromise between ride and handling. A double wishbone suspension gives you a better or an independent ride and handling characterization. So you will be able to have better handling without compromising on ride, right? So you're able to commonize the suspension between the front and the rear. You're also able to reach a good balance between ride and handling with a double wishbone. This is why most of the cars use a double wishbone. In the industry, of course, where we have a lot of resources, we use different suspensions in the front and the rear, where a lot of other factors are involved. But in racing, we mainly use a double wishbone in the front and the rear. The only difference between the front and the rear suspension would be the toe link, right? So the toe link is the link which joins the knuckle to the steering system. So your toe link would be something like this, and here your rack would start. So this is the rack, and this part is the toe link, right? So in the front suspension, your toe link would be connected to the rack, and as the rack is moved, the knuckle rotates, and hence you get steering ability at your front suspension. In the rear suspension, what you do is you just attach the toe link to the chassis. So this link would also be fixed to the chassis in the rear suspension. So the steering ability in your rear suspension is not there, right? So the only difference between the front and rear suspension is the toe link. And even in the toe link, you would have just the length of the toe link that is varying, and we will look at how the length of the toe link influences bump steer, but basically it is only the toe link that varies, right? Okay, we'll get back to this in the coming slides. The nature of wheel movement or path is very important in the handling behavior and sensitive to the location of the connection points. So when I say wheel movement, I'm talking about kinematics. Kinematics is again a different nomenclature for toe and camber behavior, of how the toe and camber of the wheel changes with suspension, bounce and rebound movement, right? So the toe and camber of the suspension depend on the toe and camber movement of the suspension depend on the bump and rebound travels, of the suspension. It also depends on the hard point locations, the locations at which you mount the suspension arm onto the chassis, and it also depends on the bushing properties, right? The elastic bushes that you have put, right? So to control the toe and camber behavior, we would like to optimize the locations as well as the bushes, right? So what would be the best locations and bushes to get the optimum toe and camber of the suspension? This would be our focus to optimize the toe and camber by varying the location of the attachment point of the arms to the chassis, right? So small changes in the geometry can make important changes to the movement of the wheel. So by varying these locations even by a small amount in the X, Y, and Z directions, so by moving each point in different directions, you will be varying the toe and camber behavior of the suspension, and you will be surprised to see how even very little amount of changes would result in significant changes in toe and camber behavior. Hence, the position of these points are critically important. The point where the suspension arms are linked to the chassis. Also, the points where the lower ball joint LBJ and the upper ball joint UBJ, the position of each of these location is critically important to the kinematics of the suspension, right? So let us look at how we can optimize these locations and do it in a practical way. So that would be the aim. So we would like to analyze the suspension under two main behaviors, which is first is the translational motion, that is bump and rebound. That is when both the wheels go over a bump. Both the wheels are going purely in bump and in rebound. And the other is the cornering motion, where the chassis is rolling. So we would like to study the kinematics under bump and roll, right? And if we are able to get the optimum angle, uh, optimum kinematics, basically toe and camber under these two conditions, we would have a great suspension. All right. So let us see at how to tune the toe and camber under both the conditions, right? All right. So when we say so, when an OEM says kinematics, there are around 25 metrics that they tune, right? And they see every minute part in the suspension, right? And that is because they have a lot of resources with them. For BAJA and FSAE, we will cover the main parts that you need to optimize. Okay, if you can optimize these three values in a suspension, that is the camber, toe, and wheel rate, you would be able to make a 80% efficient suspension. So you should have a good toe characteristic, good camber characteristic, and a good wheel rate. If you have nailed these three in the suspension, I would say that it would be a good enough suspension, because going for all the 25 different metrics is just not feasible at a student level, right? So let us see what is practical and how do we optimize these three angles. So we'll start with camber. Okay, since the start of the presentation, I've been talking about optimum angles. A lot of students have a question saying, what is the optimum angle? Okay, if I don't know if some of you guys were there in my vehicle dynamics course, but a lot of students have this question: how much of toe should I keep? How much of camber is the right camber for my vehicle? What is the right amount of bump steer? that I should have in my suspension, right? We have been talking about optimum angles, and now let's see what is the exact amount of optimum angle and what is the characteristic for the optimum angle, right? So what is the relationship? So as I said at the start of the presentation, you know, the only focus here is to maximize the force that a tire can produce. I want to maximize the force, and I will do, or I will maintain the wheel kinematics such that the kinematics help me in maximizing the force, right? So the camber angle, the camber angle can be used to maximize the cornering force. Okay, so this is just the definition of camber angle, and okay, this is when camber is said to be positive if the top of the wheel is leaning outwards. So, you know, as you can see over here, if the top of the wheel is leaning outwards, this is called as a positive camber. And if it is leaning inside the vehicle, so this is the track of the vehicle, the track. If it is leaning inside, it is said to be negative, right? So this is just industry conventions. It is good if you know this, right? This is the important part over here. For maximum grip during cornering, both the inner and outer wheels should point towards the center of the turn. So this is the takeaway from this slide, right? So if you're turning the vehicle, if you're turning the car, your camber can give you a very good advantage for maximizing the force that a wheel can, the cornering force that a wheel can produce, right? So what this line over here says is, say you're looking at the front view and this is the center of the turn, right? You have two wheels in the front and the rear. You would like both your wheels to be pointing in this direction, right? The car is coming outside the screen, right? So you would like to have both your wheels such that the top of the wheel points towards the center of the turn, the inner and the outer wheel. So this phenomenon is called as camber thrust. Okay, camber thrust is a phenomenon wherein the camber angle, this camber angle produces a lateral force, right? So if you want to know more about camber thrust, you can go through Gillespie. Yeah, it's a very simple concept, but what it basically means is that when a tire has a certain camber angle, it produces a camber thrust, right? So the more the camber angle, the more the camber angle, the more is your camber thrust. The more is your camber thrust, the higher is the cornering G that you can get with your vehicle. So ideally, you would like your tires to be like this during cornering, because this tire produces maximum force, right? During cornering, I would like to maximize my camber angle, and it is not any kind of camber angle, okay? Note this. The outside of the wheel, the upper of the wheel needs to point towards the center of the turn. If you have a suspension in which your wheel becomes like this, and this is the center of the turn, TCD, and if you have the opposite kind of characteristics, then obviously you're going away from peak performance, because here your camber thrust would be in the opposite direction, right? So this is the direction of your lateral force, whereas you require force in this direction, right? So if you have the opposite characteristic, then you're going away from peak performance. So what you would ideally like to have during cornering is to maximize the camber angle in the right direction. That is critically important, and we will do this in the coming slides, right? How do we achieve this kind of characteristic? Okay, so this was for just a second. Okay, so this was for cornering. Okay, this was just for cornering. Remember, we have three main maneuvers: cornering, braking, and acceleration. Okay, so during cornering, I would like to maximize the right kind of camber. During acceleration and braking, peak grip occurs at zero camber. That is, when your vehicle is going in straight ahead condition, your wheel should be absolutely perpendicular to the ground, right? This maximizes the contact patch area, and hence it maximizes the amount of force that your tire can produce, which maximizes the G level at which you can either accelerate or brake. So look at the conflicting requirements that you have from a vehicle dynamics perspective. During cornering, you would like to maximize camber, and that to a particular type of camber, whereas during acceleration, you want zero camber, right? During acceleration and braking, you want zero camber. So let us see what is the best possible thing that we can do. Remember from the beginning, having an ideal suspension is the holy grail. So this is the objective, this is the ideal, this is the aim towards which we should move. We should go towards it as far as possible, right? And let us see at which compromise would be the best compromise, right? All right. So before we start designing the suspension,
Vivek?
yeah,
so there are certain questions. So can we take a 2 or 3 minute break and answer these questions?
absolutely. Let me just. Yeah.
Okay. I'll read out the questions for you.
Sure.
The first question was, so the hinge on a UCA, it's from Arshad Khan. He was asking, hinge on UCA is different than a UCA. What is the reason for it? So
the hinge on the UCA is different from the UCA.
Than a UCA. So I don't know what he meant. Arshad, if you want to repeat that question, please repeat so that we can ask it to Vivek. So in the meanwhile, I will also ask other question. So Shailesh asks, during cornering, should we consider banking of roads or not?
Absolutely, you should. It's not just so. All your angles are measured with respect to the road surface. So if your road is like this, then your camber angle is measured with the perpendicular to the road, right? So this becomes the perpendicular, and if your wheel is like this, so this becomes the angle. So if your road is banked, you need to consider the bank as well, because the angle is measured with respect to the road surface. It is not the absolute vertical. The normal to the road should be considered.
Okay. So Arshad was asking, the hinge on UCA is different than a LCA. Is that so?
Absolutely. So what do you mean by the hinge? Is it this point over here?
Yes, I think he's meaning the same.
Okay, yeah, they should be different, right? Because the hinge, or I think what you're trying to say is the bracket on which the LCA or UCA is mounted depends on how much load or how much forces the LCA and UCA resist, right? Generally, the LCA or the lower control arm resists a higher amount of forces. So they are generally more sturdier than the UCA, which is more for kinematic purposes and hence can be lighter. So this is why the construction of the LCA and UCA hinges are quite different.
Okay. So guys, if you have any other questions, put it out. At 6:35, we will go back to the presentation. Yashwant asks, what is the critical angle of toe and camber?
So that is so this is what we are going to cover now. What is the optimum angle of toe and camber? So if you can just wait for that, we will cover that angle in the slides.
Super. Great. I think you can go ahead, Vivek. There are no more questions. I think, yeah. So there are some questions coming up, which we can take it at the end of the workshop. So you can go ahead, Vivek.
Sure, Sudhir. Okay, so let's continue and see how can we get the optimum angle for toe and camber. So there's a lot written over here. Let me just explain this in brief. Okay, so a easy way to do suspension design is to design the front. So there are two views of the suspension, which is called the front view swing arm and the side view swing arm. Let's see what the swing arm is and how the swing arm concept can be used to define a suspension, right? So a double wishbone suspension is basically a little complicated four-link mechanism, right? So I'm sure most of you in your engineering would have studied a four-link mechanism, right? And this is your ground link on which the other three links are mounted. So your double wishbone suspension is also a four-link mechanism on which here your wheel is there, right? So when we studied the four-link mechanism, you would have also studied regarding things called as the instant center, right? So how you get the instant center is by extrapolating these two links, and the point where the two links meet is the instant center for the mechanism. What the instant center is a point about which the entire mechanism is rotating, right? So if you remember in rigid body dynamics, for a sphere which is in pure rolling condition on a surface, this was the instant center, right? So at any point, the entire wheel can be considered to be rolling about this point. The same motion can also be considered in this way, that it is rolling about the center of mass as well as a translational motion of the center of mass. But at this point, the entire vehicle is in pure rotation. That is, this is the instant center. Similarly, for a four-link mechanism, this point or the instant center is the point about which the entire suspension or all the three links are in pure rotation, right? The instant center it becomes useful because it helps us find what is called as the roll center, right? During cornering, what happens is the suspension doesn't move up and down. Okay, what is happening is that because of the springs, because of your springs and lateral force which is acting on your chassis, the chassis is rolling. Okay, and the chassis is rolling about the tire contact patch. Okay, so the tire contact patch can be said to be at one point, and about which the about the wheel track and the tire contact patch, your chassis is rolling. So when we connect the instant center to the tire contact patch, you get a point on the vertical plane which is called as the roll center. The roll center is the point about which the lateral force which is acting on your chassis is reacted by the suspension, right? And for all practical purposes, you can consider the chassis to be rolling about the roll axis, which is the axis which is created by joining the front roll center and the rear roll center. Right now we are considering just one suspension, so there is just one roll center, right? So basically you need to find the instant center, and from the instant center you find the roll center, right? Once we have the roll center, now we can find the camber and the other metrics, right? So this slide just shows you how to find the roll center, right? All right. So now this is the fun part of suspension design. We are in the front view suspension design. Let us start with, so let me take you through a step-by-step process of how we come to a final suspension. We will start with, please look at, please pay some attention to the terms that are used over here. Parallel equal link double wishbones. So the two links are parallel and they are of equal length. Okay, we are starting off with this design, and let us see what is the performance that we get out of this suspension. Okay, and before we go ahead, let me just say that all this is done on a graph sheet. Okay, You don't have to do anything else. And if there is time by the end of the workshop, I would like to show the same thing in a software package. I'm comfortable with Adams, MSc Adams, because I've been using that for 10 years now. So I will show you the same thing in Adams as well. But I would leave the software choice on you. If if you want to use a software package, you can use anything, Motion Solve or Simpack, anything that you have it in your campus or something. But I will be showing you the examples in Adams because I'm comfortable with Adams. No other reason. Not that Adams is the best or something, but I'm comfortable with Adams. Okay. So right now we will do it on a graph sheet. Okay. So we start with equal parallel link suspension, and we would like to see the performance or the camber values. Right now we are dealing with camber only. We would like to see the camber for a parallel equal link double wishbone during roll. So this graph over here is for roll, and this is for parallel, that is bump and rebound travel. Okay, let's see it for roll. Okay, so during rolling, as we know that during rolling the chassis rolls. Okay, we are considering a chassis roll of 4 degrees. Okay, the from the last slide we know that the chassis rolls over the about the roll center RC. Just note over here that the roll center over here is at the ground level. Okay, this is because of parallel links, right? So if you have a parallel link suspension, the instant center is at infinity, right? Because if you extend the two links, they don't meet. They never meet. So we say that the roll center is at infinity. How do we get, no, the instant center is at infinity. How do we get the roll center from instant center? We join the instant center to the tire contact patch, right? So since the instant center is at infinity, the roll center, so when you take this line, the tire contact patch, you're trying to join it to the roll center, which is again at infinity. It's very, very long, far away. So your roll center is at the road level itself. So this is just the logic behind why the roll center is at ground level for a parallel double wishbone suspension. So the roll center is at the ground level over here, and note that the chassis is rolling by 4 degrees. Okay. The chassis rolls by 4 degrees. Now the question is, how much of camber will this roll produce? Okay, now this is super easy to find out. Let me just show it over here. Okay, so what is happening over here is that this is my initial condition. I have a parallel link. Okay, and then what happens is it rolls by some angle, say theta. I've given a exact value over there, 4 degrees, right? And I would like to see what is the camber value, right? So what happens over here? Say if this is theta and this length is say A, and this length is B. Okay. So this point, so this is rolling, right? So the chassis is rolling about the RC, which is at this point, right? Due to rolling, so again we are going to use this formula over here, right? The R theta, this can be either A or B. So if this is theta, this is A or B. This can be approximated to a straight line, which is A theta or B theta, right? A theta or B theta. So this point would move in this direction by A theta, and this point would move in this direction by B theta. Since theta is the same, B is greater than A, so this point moves here and this point moves over here. B theta is more, A theta is less. right? So your final, after rolling, this link would have come over here like this, and this would have come over here, right? The length of the links are the same, just that the chassis at this point moves by a lesser amount than the chassis at this point, right? We are ignoring the translational displacement due to the arc, okay? Since we are on a graph sheet, we are not using a software program, and this is a reasonable approximation because of the length of the arc. So, I hope you understand the approximation. This formula is valid for an arc. We are basically saying that it is a straight line. That is the only approximation that is over there. So this is ignored, right? So basically the upper uj moves by a larger amount than the lower lower link attachment point, and then you get, and this is the link which is already present. So this angle is so your wheel becomes somewhat like this, right? So what is and this angle is your camber angle with respect to the vertical. This angle is your camber angle, and what is that angle? So if you just join this, and if you see this angle is also theta over here, right? So basically what happens is it becomes a parallelogram where this angle is theta and this angle is also theta. So your wheels get a camber angle of theta if your chassis rolls by theta, right? So if you use equal link suspensions, you get the same angle of camber as the body is rolling, right? Now let us see whether this is beneficial for us or not. Okay, so what we have seen is that the amount of camber that we get during body roll is the same. So what you'll see is that you're having the same amount of camber as the amount of roll that you have. Now the question is, that is fine, but am I getting the right kind of camber? Okay, am I getting the right kind of camber? Now look at this in more detail. Your body is rolling in this direction. Okay, that means your lateral force is acting in this direction. That means your center of turn is in this direction. Your vehicle is coming outside and it's taking a left turn for everyone who is sitting in front of the screen. Your vehicle is coming outside the screen and it's taking a left turn, right? So this is the center of the curve. As we had seen from the earlier slides, your wheels need to be cambered towards the center of the turn, right? So that you benefit from a phenomenon called as camber thrust, right? If you devise a suspension which has equal links, you would have a good amount of camber. You have a large amount of camber, 4 degrees of camber, which is a lot of camber. You have a large amount of camber and you have a camber which is in the wrong direction. So instead of helping you with performance, this kind of suspension during cornering will actually decrease your performance, right? Because in this case, camber thrust would be acting in this direction. These forces are the tire forces due to slip angle. So, we will cover slip angles as well, not in this workshop, but when we look into the course, when we are doing tires, we'll see at how to manage the slip angle as well. You won't be benefiting from camber thrust, which is what we have been trying to do, right? Because camber thrust is an important part with this kind of suspension architecture. So this was during roll, okay? Let's see what happens during parallel. Okay. During parallel, as you can imagine, with equal links, you get zero amount of, so your chassis is basically fixed over here. Chassis is fixed, only your wheel is traveling up and down, right? So as you can imagine, if you have a equal, sorry. So if you have equal link, so if you have equal links, and if your wheel, sorry again, this is absolutely vertical. If your wheel is just moving up and down, okay, you can say that the camber is zero continuously, right? So this is the position when your wheel has gone up by whatever amount. So, basically your links are parallel to each other, they are of equal length. So they produce no adverse camber during just bounce or rebound. During just translational motion, you have no camber at all, and this is very good, right? So as we have seen that during um, wait a second. Sorry. Okay, yeah. So during bump and rebound motion, we would like to have zero camber so that the contact patch area is maximized and hence your tires will be able to produce maximum forces, right? So a parallel link suspension is very good if for acceleration and braking, but it decreases your cornering performance significantly because instead of having camber thrust benefit you or produce more forces, you're actually having camber thrust, which is reducing the amount of lateral force that you can produce, right? So this is what is actually written in all these words over here. I just go through them. I'm just explaining it. Hold on. It does not maximize grip, but it actually goes in the opposite direction, right? So if you are going to use so what are the things that we can, so we have a perfect situation in uh, acceleration and braking, okay, that's the perfect situation. What can we do to improve the suspension during cornering, because cornering is one of the three maneuvers, right, and we would like to have peak performance during cornering as well. So what can we do? The first solution, so these are the different solutions that I have proposed. The first solution is to stiffen the springs and the anti-roll bars to reduce the amount of roll and hence the amount of adverse camber. So, with the current set of springs, if you are having 4 degrees of camber, you really stiffen up your springs and anti-roll bars so that you get just 1 degree of camber, right? So 1 degree of roll, which would also result in just 1 degree of adverse camber. Again, you're not helping, but you're going in the wrong direction, but a little less in the wrong direction. Instead of having 4 degrees worth of bad camber, you'll have 1 degree worth of bad camber. You have increased the situation to a certain extent, but not completely as possible. This is also a bad solution because spring should be as soft as possible to so that your suspension is able to follow an uneven road. So unless you have a road which is absolutely flat, you generally roads have certain undulations, and for a suspension to follow those undulations and to maintain contact with the ground, you would like to have springs which are as soft as possible. So what you'll see is that in passenger vehicles, springs have the function of comfort. Springs are installed so that we have maximum comfort in cars. But for a race car, springs are used to optimize the grip between tires and road. And that is the function of the spring in a race car. And we will see that maintaining a soft spring will help us in maintaining grip as well, right? So Spring should be as soft as possible, but there is a minimum limit. We will see that during the, when we go into springs and anti-roll bars in more detail. Not here. Otherwise, what the second solution that I've proposed is that we can add a static camber, right? So in all these diagrams, so static camber is the amount of camber that can be put before the suspension goes into motion. Basically, what it is like this. So when your suspension is just sitting, it's not running, your car is in static equilibrium, the amount of camber that your wheel has with respect to the road is called the static camber, right? So before your vehicle runs, you can adjust the link position such that your wheels have a certain amount of camber angle, right? That is called your static camber. We can add static camber. In this case, the wheels had started out with -4 degrees, right? If the wheels start out with -4 degrees, okay, that is to say that you have wheels which are like this, right? So, just a second. So you have wheels which are like this. Sorry, I mean -4. -4 would mean that your wheels are like this. Both the wheels are pointing inside. This, sorry, this angle being 4 degrees. So -4, right? So this is the amount of static camber that you have given, right? During rolling, what happens is that this wheel, so this wheel over here, which is going into positive camber, will go from -4 degrees to 0 degrees. So one of your wheel goes into 0 degree, which is a good thing, and the other wheel goes into -8 degrees of static camber, right? So your outer wheel goes into 0 degrees. So in all our design conditions, we will be considering on the outer wheel because the outer wheel is the loaded wheel. During cornering, load is transferred from the inner wheel to the outer wheel. Hence, your outer wheel produces the maximum amount of cornering forces. So again, we will be considering the outer wheel itself. So if we have -4 degrees of static camber, after rolling of 4 degrees, the roll produces a camber of +4 degrees. So after rolling of 4 degrees, your outer wheel would become completely vertical, that is perpendicular to the ground. So in this case is also not the optimum case because as you remember, we would like our wheels to point towards the center of the turn, right? So after rolling, we would like the wheel to point towards the center of the turn. But of course, this is a better situation than what we started out with, right? Because the outer wheel now is at least perpendicular to the ground. But can someone tell me what is the disadvantage of this? One of the main disadvantages of this is that if you give a static camber of -4 degrees, first of all, -4 degrees is a large amount of camber. If you give a large amount of camber, this large amount of static camber to your wheels, then during straight line running, so during parallel wheel travel or straight line running, your wheels would continuously point like this in the front view, right? So one edge of the wheel is continuously being worn out and you would have issues of tire wear. You would continuously need to change your tires. So look at how we are compromising over here, okay? In the first case where, we had zero static camber, we had a very good situation with acceleration and braking, but our cornering was bad. After adding static camber, our performance in straight line has deteriorated because of static camber. The area of the contact patch has reduced, and the amount of forces that your tire can produce has also reduced. But the cornering performance has increased because your outer wheel is now perpendicular to the road, right? So in an attempt to improve the cornering performance, we have degraded the acceleration and braking performance by adding a static camber. So even this is not a great solution. Even this is not a great solution. So what can we do? These are the two things that are generally done. We can use a converging link instead of parallel links. So realize that we started off with parallel links, parallel equal links. Let's see what happens when we use converging links instead of parallel links. And also we would, if you use a shorter top link instead of equal links. So let us try these two methods and see how the camber performance is tuned, right? So this is what we will see now. All right, so again, we're going to consider the same case. We have 4 degrees of roll. So this is for roll and this is for parallel. Instead of having parallel links now, we have converging links. So they meet at a certain point, right? What we are assuming over here is that the swing arm length is equal to the track length. I've just taken this assumption so as to make these values, right? So that you have a better idea of what the numbers that we are talking about, but they can be of any length, right? So again, the same thing that we are going to use. First, we have converging links. You can find the instant center, then find the roll center. In this case, the roll center is over here. Note that it is not on the ground because the instant center is not at infinity, right? So we have a roll center and the chassis is rolling about the roll center. It has rolled by 4 degrees, right? And again, you use the same process that we used earlier on, basically by rolling by 4 degrees, this moves by A into theta, this moves by B into theta. And then you find the camber angle that your roll produces. So this entire thing can be done on a graph sheet, right? So again, the same thing, we have converging links now. It's rolling again, A and B. It rolls by theta about the roll center or the RC, right? Again, we approximate that the arc is a straight line. This moves in this direction by B into theta. This moves in this line by A into theta. This becomes the final position. Okay, so since B into theta is more than A into theta, this is reasonable. And it becomes like this. So this becomes your final position of the suspension, right? And this angle is your camber angle. So if you plot it on a graph sheet correctly, you know the length of the links. You know these positions from A into theta and B into theta. You know the length of the links, right? And then you join these two points. And then you know the angle that this link makes with respect to the vertical, which is nothing but your camber angle, right? So this is some theta dash, which is your camber angle. So if you just do this, you will see that with a 4 degree of roll, your outer wheel goes into just plus 2 degrees of camber angle. Remember that this was plus 4 degrees in the previous case, okay? And now it is at plus 2 degrees of adverse camber. So what we call this is 50% camber recovery, right? So instead of going into plus 4 degrees of camber, your suspension just goes into plus 2 degrees of camber, okay? And the important thing is now you can give a minus 2 degrees of static camber so that your wheels will be in perpendicular direction in peak cornering, right? And with this, instead of giving just, earlier we had to give a minus 4 degrees of camber, right? And right now we just have to give minus 2 degrees of camber, which is better than giving minus 4 degrees of camber for your straight line performance, acceleration and braking, right? So by using converging links and by what happens by camber recovery is a term which has been coined, you are improving the cornering behavior while not compromising your straight line behavior, right? Uh, so it is a little better, right? Uh, So this is why in most of the race cars you will see converging links of suspension. In fact, in some of the students have used pretty bold suspension designs like this, where they are completely converged onto one point. They're called Lancaster links. So you have a suspension like this, right? So they're completely converged. Here still we have a certain amount of gap, but this is completely converged, right? This is just to take care of camber recovery, right? So ideally, we know how much of camber, during cornering, I would like to, if not have a negative camber in my outer wheel, I would at least like the outer wheel to be perpendicular. And during straight line motion, I would like to have zero camber for my wheels, right? So that is the objective now. Okay, so when we talk about optimum angles, what is the optimum angle? It is 0 degrees for acceleration and negative camber for outer wheels. If you can't reach negative camber, at least try to have perpendicular wheels or zero camber for the outer wheels. Remember one thing, that you are not designing your suspension for just cornering or for just acceleration and braking. You're designing a suspension for all three maneuvers, right? So there is a compromise between cornering as well as straight line motion, right? And I think if you have this kind of a suspension in your vehicle, then you can put this suspension with say minus 2 degrees of static camber, right? You can put it with minus 2 degrees. So this is assuming you have 4 degrees of roll during peak cornering, right? So you can put in this suspension with minus 2 degrees of static camber so that during cornering, your outer wheels would be perpendicular, maximizing the grip. And during straight line motion, you would have minus 2 degrees of camber, which is slightly better than uh, minus 4 degrees of camber as seen earlier, right? And maybe if you can reduce the roll to a certain more extent by using a better ARB, so you can maybe go ahead with a minus 1 degree of static camber, which is pretty good, right? So this is where the tuning part comes into play, and this is where the driver also gets involved with the race car, right? Uh, yeah, so let's continue. All right, so this is the final thing. Generally, what we use is converging unequal links, right? So the upper link is generally shorter in length than the lower link. The reason being that this helps in dialing down the roll center vertical movement. So what you would see is that if you find out the roll center height as the wheel moves up and down, you would, so obviously the roll center depends on the instant center and the instant center depends on the position of the links. So as your wheel moves up and down, your roll center is also moving in all the directions. It's moving up, down, and laterally, right? We would like to minimize the roll center movement, because as your roll center moves up and down, even the amount of load transfer that is happening between your inner and the outer wheels also changes, right? Because your chassis is basically rolling over the roll center, right? So we would help, we need to dial down the roll center vertical and lateral movement. For this to happen, we generally use unequal links. So the upper link is generally shorter than the lower link, right? So this helps in reducing the roll center vertical and lateral movement. So this is why you would see this kind of a suspension in most of the race cars, right? That is converging unequal links of suspension is generally used. Uh, right. So this concludes the camber part of the suspension. Let me just give you one slide about the toe part as well, because toe is also critically important. So for toe, what we have again is that for straight line motion, we would like to have zero toe. Okay. For acceleration and braking, we need to have zero toe. Okay. Absolutely zero, which so the static toe that you have is zero during acceleration and braking. What happens during longitudinal motion due to suspension travel in vertical direction during bounce and rebound of the suspension is a problem called as bump steer, right? The As the suspension moves up and down, the wheel toes in and out if you haven't designed your suspension for bump steer. Okay, so what is bump steer? Basically, if you plot the wheel travel versus toe, okay, what you would like to have is just your static toe. This is your static toe. That is, your toe doesn't change with wheel travel. But if you haven't designed your suspension correctly, you would have a toe value which is like this or like this in any direction. That is, your toe changes with wheel travel, and that is not required because we would like to maintain zero toe with wheel travel, at least in the vertical direction, right? So how do we achieve that? Okay, what just happened?
Just share it once again. Share your screen once again,
Okay,
Vivek.
okay. Okay. Uh, so how do we correct for bump steer over here? So basically the bump steer can be adjusted by placing your tie rod correctly, right? So your tie rod, this is the side view of the, this is the front view, I think. Yeah, this is the front view of the suspension. Okay. So this is the upper ball joint. This is the lower ball joint. So the upper ball joint, lower ball joint, and these points are connected to the chassis. So this is connected to the chassis, and even this is connected to the chassis, and these are my ball joints at these ends, right? So by placing the tie rod correctly, you can avoid bump steer, right? So let me just give it to you in brief. So how do we place the tie rod is that join these two points, the two ball joints, and join the points on the chassis. Okay, you can place the tie rod such that the two ends of the tie rod are on these two lines, this line and this line, and the tie rod needs to pass through the instant center of the suspension. So this can be a tie rod where okay, again something has happened. Let me share it again. Okay, so you can have your tie rod basically needs to be between these two lines, this line and it needs to pass through the instant center. So so even a tie rod which is like this is perfectly fine because this would pass through the instant center, right? So this point as well as this point, right? So this can be your tie rod, and with this tie rod, you would have zero bump steer. To understand this in detail, I would say understand the four-link mechanism. I guess some of you can already visualize this, but if not, just go into the four-link mechanism details, and you will be able to understand this, right? So by positioning the tie rod properly, both the length as well as the position, you can avoid bump steer and hence maintain the toe angle, that your car should maintain. So let's again talk about optimum angles over here. For acceleration and braking, your toe should be 0 degrees, absolutely vertical. Your wheel should be, right? And for cornering, don't rely on toe to optimize cornering. Okay, don't go to toe to optimize cornering. Instead, use steer angles to improve cornering. Steer angle is the angle that your steering system produces due to rack motion. How much of steer angle is produced, right? So this is the optimum angle for toe. And again, this can be done on a graph sheet again. Okay. All right. So let us conclude this, at least the theory part of it, by summarizing what we have done till now, right? So we would like to maintain good camber control during roll. That is by using converging unequal links of suspension and providing enough static camber to avoid a positive camber on your outer wheels, right? To provide a stable roll center location, we would like to use unequal links of the upper link and the lower link. Instead of having equal links, we would like to use unequal links. To minimize the scrub, we would so the lateral displacement of the tire contact patch should be kept at minimum. We can see the tire lateral behavior also in detail, maybe in the course. This is covered in the course. Let's not go into it. So we would like to maintain good camber control during bump and rebound as well as suggested. The ideal value is 0 camber, but this is obviously not possible for a suspension that we are designing. A true compromise would be to use an active suspension which would produce optimum results. So maintain 0 toe and 0 camber for straight line. It reduces tire wear and it maximizes the tire contact patch area, right? So that's the best suspension that you can have. Okay. Uh, so I think this is the front view requirements of the suspension. Similarly, we can have the okay, side view requirements, front view requirement, and okay, guys, before we go into the Adams part of simulation, I would just like to show you this as well, which is again a very theoretical thing that we can do. So, you know, for suspension design, the kinematics is important, definitely. That we have been, that we saw just, we just saw the position of the links and the length of the links important for the tie rod. But what is also important is what is called as the durability, right? Structural durability of the suspension components, right? So before you can evaluate the structural durability of the components, you need to find how much of forces are coming onto the components, right? So mainly we consider three main. So you know, this course is about complete design of the suspension. It is not just the kinematics, but it is also about you know, how much of forces come onto the suspension and whether a suspension is truly durable, right? That is, your suspension component shouldn't break. So to evaluate the structural durability of the suspension, we need to evaluate the loads which are coming onto the suspension. Okay, let's look at that. So I'll just explain it for one load case because I think we are already exceeding time. Maybe we can do this in detail during the course itself. So let's see the 3G vertical loading. So this is a load case which, you know, basically your vehicle is going in a straight line and you have a sudden bump onto your suspension. You know, we generally say that that is 3G loading, saying that the amount of force that comes onto the tire contact patch is 3 times the FAW or the front axle weight, right? So, you know, before you put your cars onto the field, you would probably measure the load coming onto each of your corner, right? So that would be the FAW by 2 for that corner. right? So 3 times that force is the assumed value or the maximum value that can come onto your suspension, all right? So we give this amount of force at the contact patch, and the aim here is to find the force, is to find how this force is reacted by the suspension, right? So this is where your FBD skills come into play. Free body diagrams, Newton's second law. So if you are good with FBD, you can just follow this very smoothly. So basically, how does this force go into the suspension? So this vertical force, a vertical force is mainly resisted by the springs, right? So you have a vertical force. This total vertical force is resisted by the spring which goes through the bell crank and the arm, which is connected to the bell crank and the lower arm, right? So you have something like this. You have a vertical load, and this is your arm, which is resisting the force in this direction. So what you'll see over here is the arm is over here, the length AB, right? So your arm reacts the force in this direction. So the total force which your arm takes is in this direction. It is along the link, right? So you know the force which your link takes, right? Once you know the amount of force that your link takes, there is a horizontal component due to the push rod, which we saw over here. This horizontal component is distributed between C and D. The distribution between C and D depends on the location of C and D. So you have one force, if you have a force over here, how do you distribute, how is this force reacted between C and D? Depending on the distance of C and D from A, this force is distributed between C and D. And hence you know the total force at A, C and D. This total force can be given into a FE program like Nastran or Abacus, and you can see the stresses which are coming onto your component, right? So this is theoretical way of getting the forces. I will, I'm just going through this really quickly because there's so much to cover over here. I would like to do this in, actually this entire slide would take 1 hour to explain properly. But unfortunately we don't have that kind of time. So let me just explain, the same thing in atoms, whatever we have seen right now. Okay. So let me just explain the entire thing in atoms, and then we can break for the day. All right. So let's look at suspensions, and let's look at full vehicle, right? So
Just stop and reshare. Vivek. Yeah. Vivek, you're on mute. Let me unmute you. Yeah, I think you're on unmuted.
okay. Okay, so let us just start with, I'll show you the camber behavior, right? So I have a full vehicle over here. This is the default suspension assembly. This is the default car in Adams. It's accessible to everyone. Just a second, guys. Hey, Surya, I would like to move this bar. How do I do it?
Just drag it, Vivek. Just drag it.
It's clicking on a button actually. It's clicking on all the buttons.
Or minimize your screen. Just minimize your. Yeah. Now.
Okay, fine. Let's do this. Okay, so let's start off with the suspension assembly. Let's just call this test. Okay, so just look at the suspension over here. We'll just demonstrate what we have done. We have parallel link suspension over here. Okay, so we have parallel link of suspension. Note that the tie rod, which is the gray part is the tie rod. So the tie rod is also parallel to the links. Okay, so since this is a half vehicle, let's see the toe behavior. Okay, so if we need to see the toe behavior during parallel, we do a parallel wheel simulation, right? We'll do a test. Let's take it to 100 mm of, let's take around 60 mm of bump travel and minus 40 mm of rebound travel. Right? So what we have over here is a parallel, all the links are parallel to each other, and we should be ideally having zero bump steer over here. Okay. Now let us have a different case wherein the tie rod is not positioned properly. Okay. That is, if you don't have the right position, let us just change it in Z by say 20 mm. Okay. Now what you're seeing over here, just look at this. Your tie rod is not parallel to the links anymore, right? So let's call this unparallel. Okay, and let's run the same simulation again, and let's see how the toe characteristic has changed. Okay, during parallel wheel travel, right? So understand that we would like to have zero toe, that is to position the toe link correctly. Okay. I hope you guys are able to see the post processor. Uh, Surya, the post processor is visible, right?
Yes, Vivek.
Okay, great. So first, let's see the unparalleled links. So one good thing about Adams is that you don't have to make these. So these things that you're seeing over here, the request as it's called, these are pre-made in Adams. So you don't have to make requests for basic things like toe, caster, camber. All these are already there, and you can easily use them. Uh, so look at this, okay? On your x-axis, you have wheel travel, and on your y-axis, you have the toe angle. Look how your toe is changing with just parallel wheel travel, okay? That is, your wheels are going up and down, and your toe is varying. This is the problem called as bump steer, okay? Ideally, I would like to have zero bump steer. That is, my toe shouldn't change with wheel travel. Let us look at the test run that we had done, in which we had parallel links. Okay, look at how we have minimized the amount of toe. So in the earlier case with unparalleled, we had 1.5 degrees of toe, which is significant. Here we have 0.5 degrees. And I'm sure if we tune it a bit more, we can really dial it down to say 0.2. Ideally, we would like to have 0 degrees of toe. Okay. So this is the problem of bump steer, and how we solved it was by changing the the length and position of the tie rod are the most effective ways of solving the issue of bump steer. Understand this, okay? So generally we change either the outer tie rod ball joint or the inner tie rod ball joint. Here we had changed the inner tie rod ball joint, right? So you can change this as well. This point over here, that can also be changed. So this point, this point can also be changed, or this point can be changed to solve the problem of bump steer, right? Let me just give you a last example for camber recovery, and then we will call it a day. So let's go to the full vehicle now. Just to give you an example of full vehicle also. Yeah. So once you do a KNC properly at half vehicle level, we would like to do full vehicle simulations, right? So again, as you see over here, we are starting off with, uh, you know, parallel links of suspension. So we have parallel links. Look at the upper link and the lower link. They are parallel to each other. Okay, let's do a full vehicle simulation. What happened?
I think you need to reshare.
Okay. So let's do a parallel link. So we'll do a cornering simulation, a constant radius cornering. Let's call it parallel links. Okay. We'll give our output step size of 0.1. Our turning radius of 33 is standard in the industry, 33 meters. We'll take a left turn. Let's vary the we'll keep it a small simulation, maybe for 20 seconds. From initial acceleration to final acceleration. Let's give this a try. So this is with parallel links in the front suspension. Okay, and let's see what is the amount of camber angle that we have. And then we will go to converging links, which produce a better camber recovery. And let's see what's happening. So right now we are doing a constant radius cornering test, which is a standard test to measure the understeer gradient of a vehicle. For those people who are not aware of understeer gradient, we'll be doing that in more detail in the course. But a CRC test or SSCT, steady state cornering test, is a standard test for understeer gradient, right? Alright, so this simulation is almost done. Let us vary this point. So let us vary the lower links. So in Adams, what we have is these are called as hard points. So what you can see over here is the LCA front hard point. Let's modify that. And to make them converging, let's bring them up to say by 20 mm. And that should be sufficient. Okay. And the rear hard point also, let's bring that up by 20 mm. 205. So they have become kind of converging. Also, let's change the upper hard points, right? From 560, let's bring them down by 20 mm, 40, right? And even the upper front, UCF front, let's bring it down by 20 mm. So now we have somewhat converging, more converging than previously. And let's call this as converging links. Converging, right? So first we did the simulation with parallel links. Now we're going to do the same test with a different set of hard points for converging links. Okay. Yeah, simulation is running. So the intention over here is to avoid positive camber. That would be the intention. Let's see if converging links can help us avoid camber. So, okay, we are again, let's go to the post processor. And we have these two simulations over here. So at the full vehicle level, instead of directly searching for tow, you need to search for suspension, what's called as suspension kinematics. This way, Adams is pretty confusing because it directly doesn't give you tow. So let's see. We have taken a left turn, so we should be looking at the right wheels because the right wheel is the outer wheel, right? So we will look at camber right front. Okay, look at the parallel wheels over here. Okay, you have a larger amount of positive camber. Look at the y-axis, we are reaching up to 0.3 degrees of positive camber. Whereas with the converging links, we are still in the negative camber zone, right? So in fact, we don't even reach zero camber. We are in the negative camber zone, helping camber thrust, right? So this is exactly the kind of behavior that we require, right? So, I'm just showing you what we already saw in the theoretical. So people who are not convenient, so generally why these softwares have become popular is that they are very convenient to use. So, but you need to know what to get out of a software, right? So you know that you need to have a negative camber in your outer wheels and you're getting that. So you're going in the right direction. So even in your actual design, you can go ahead with converging links.